Hello everyone, welcome to a new Substance Designer tutorial. We will be covering loops inside Substance Designer. I already prepared a few examples here. Just to briefly mention, we have a few ways to do loops inside Substance Designer. The first one is with the while loop node inside the pixel processor. We also can do loops with the iterate node inside the fx map, and we can also do loops outside the pixel processor or fx map if we construct a certain kind of graphs for ourselves. Okay, so let me show you what we are going to um, recreate from scratch today. So we're getting this kind of effect by taking a cone gradient, and inside the pixel processor we're going to do something which is very similar to the histogram select. So from this gradient we're going to select a band, and we're going to move this band along the gradient. We're also going to offset the position of this gradient, and this will produce this kind of effect. If I go inside, you have a few things that you can play with. So for example, this is the width of the bands. If I change this value, this is going to increase the width of the bands. Let me decrease it back. We can also go in here and change the number of rings, so more or less rings. Let me put it back to 64. We can also play with this parameter, which I think it's the main parameter that would create an interesting effect. So it's creating this looping behavior, which I find really interesting. Okay, so it's doing this swing back and forth and left to right, and also changes color. So I think it's an interesting effect. Then we also have a similar effect where we take a Perlin noise and then we make a map like this out of it. And again, we are selecting a few contour lines from it, and then we elevate those contour lines gradually. And this is sort of like a 3D print effect if you want. So maybe you could see these layers. You also have this gradient that allows you to change what's really going on here. So by default it looks like this. It's essentially scanning the Perlin noise level by level and increase the levels up. I also added here a quantize and the blur. If I remove this, we're going to get the Perlin noise itself. And then if we add this, we're going to get this stair step effect. Okay, next we're going to have a few interesting examples here to show or to try and explain what's the difference between the fx map and the while loop inside the pixel processor. So they are very similar, but pixel processor has a few extra things that you can do that will allow you to do much more. So for example, let's imagine for a moment that this is kind of like a bowl that has 3 holes, and then you have a marble that starts maybe somewhere here, and then you want to find out where it's going to land, depend on the starting position. So imagine you have a bowl, and then you have a marble bowl, and then you let that marble slide inside this ball, and eventually it's going to reach the bottom. And the shape of this bowl, so to speak, has like these three holes. So let me go inside the FX map, and um, we can just reduce this to 1. So this is the starting point, and then as you increase this value, then the ball is starting to roll inside toward the bottom, and um it doesn't go straight to the bottom. It has a bit of inertia and is going to wander back and forth for a while until it's going to approach its final rest position. And this is not super physically accurate. That's totally fine. It's just for the purpose of showing some things that you can do in the pixel processor. Okay, so we're simulating based on the starting position. The marble is going to roll down the ball, and it's going to end up, for example, in this bottom place here. But I have this parameter. I have this tick here that I can change. So for example, depending on this, on the position, you can see that it's going to end up in some different places. And the final location where this lands, it's based, or it's totally determined by the starting position here. So then it would be nice if we would say like, hey, what happens um, if we would simulate like absolutely all position, what would happen? Can we get a map that would show like we have 3 different grave scale values here, and we have a starting position, and we would say, hey, if I start here in this position, um, what would be my final position where this position is going to land me, and then color this pixel, this starting position, by the final color here. Okay, so we can simulate that for all the pixels here. And this is a 2K image, so we're essentially simulating 4 million simulations, and it's really fast, and it's really interesting. So this is in the pixel processor node. We have a ball this time um, with 6 holes, and then depending on the starting position, we're going to color each pixel by its end position. Okay, so for example, these are colors for each of those bottom places of the ball, and then from each pixel is going to get colorized by the respective color. You have the possibility to change the random seed. So currently we have 4 yellow dots, which it's not the absolute best. Ideally, we would want to have this uh, individually colored or with a distinct color. I think I should go in here, and instead of using random, so instead of luminance random, I think by pattern number, something like this. And maybe just add more colors here. Put a green, for example. Yeah, maybe that's a bit better. So I'll take this gradient map here and use this one instead. Okay, so now we're getting this more colorful map. This has the qualities of a fractal. It's having a bit of chaos and a bit of cell similarity, And then, for example, you can go and change with this parameter, so you will be able to change the number of those circles, and you can see the more you have, the more noisy and chaotic it gets. Maybe with 5 it looks not too noisy, but still interesting. I'm going to leave it like this. Okay, so these are a few examples in which we used pixel processor and FX map, but then these are inside these nodes themselves. The loops are happening inside the pixel processor and the FX map. But you can also do something that it's like the while loops, but outside these nodes. So for example, we have this structure here that takes in a circle and then just take that circle and moves it around and rotates it and then adds up all these circles, and it's creating a small spiral. So you can just go inside of this one and see what's happening. We're taking the circle, we're just moving it around, and we add the moved circle with the previous input, and then we just output this thing out. So for example, I can take this transform node and change its properties, and then you can see what's really happening here, the cumulative effect of this. Also, this blend node has its opacity going on, so this is going to create for us this change in color. If I get this to absolute 1, everything is yellow. If I decrease this, then the colors start to change. Okay, that was an interesting example. You have something very similar next, but has a bit more things going on. Again, we're taking a disk and then we bring it inside and we move it, but also we blur it, and then we add the move circle with the blur one, and then we output this. And if we keep doing this, it's kind of like an animation, but you can also see how things that happened in the past, so the circle, it's doing an animation, it's starting here and then moves here, 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 and so on. But you can see how things in the past become more and more blurry. And this is creating like a trail effect, or maybe if you want to think about it, it's like a smoke effect, like this thing diffuses as time passes and gets so diluted until it almost gets completely diffused. Okay, we also have this effect where we move things around, but we also move them up and down, and this up and down movement, it's selectively chosen. So the difference from this one to this one is we now have this system here of numbers that keep tracks of the number of iterations. So it's essentially like the I++ in the loops. And based on these numbers, we can decide, for example, this has been, this is taking every other dot, and it moves the dot up, and it also blurs it. So this is essentially what this thing is doing. So we can selectively apply some actions to the incoming patterns based on this numbering system. So the blur only applies to the top ones. And you can see what's going on. So we start here, and then we change this kind in this kind of fashion. And this system, it's a bit interesting. Sometimes it becomes a bit mind-bending to think about it, because you would expect something else to happen. So we started with this, but then we made this. Things have changed, and we probably weren't expecting this initial thing to disappear, and then you can see it's more like a switch between states, which I think is an interesting effect. And then probably you can go inside, and if you do this, then you're also going to get the spiral. How to um, get rid of this kaleidoscopic effect? You need to go here into the transform node and disable the tiling. So tiling mode, absolute, and no tiling. Okay. And then I think I can also so this is again making a spiral, and this is moving like up and down. Okay, I'm going to hit a couple of undos because I think the original example was a bit more simple to understand. Then we have a similar system, but this allows you to create fractal tree-like structures. So you're taking in just a single rectangle, and then you copy it twice and add this to the original rectangle, and then you keep doing the same operation, and the tree grows more and more complex. And what's happening inside is really simple. So we're taking, and let me go to the actual beginning. So we're taking the initial segment, we transform and rotate it, we make another copy, we add these copies together, and lastly we add everything together, and then we just output this, and then we just repeat these operations, and the tree grows into a fractal, which I think it's interesting. And the last example is something a bit different. So up to this point, we used the transform node and the blur node, but let's do something else. Let's bring inside the splatter circular node, and this splatter circular node is going to be scattered around a few times. And then we also have this Perlin noise map. So the position where this let's say those are stylized flowers, and based on their position into this space, they're sampling this Perlin noise map, and based on the luminosity of this Perlin noise, the flowers are going to get more or less petals, so to speak. So you can see this one, it's sampling a lower value into the Perlin noise, and it has less petals, and this one, which is brighter, samples a higher value in the Perlin noise and has more petals. And then if you go here and change the Perlin noise, you can see how the number of petals changes, and it's based on this Perlin noise. Okay, we can also change the random seed, and then these flowers get scattered differently. And again, this is a system that we have created, and it uses already existing nodes that you can put inside of the system and basically loop over them. So we included in this looping system, we included the tile the tile circular grayscale node, and we also been able to affect some of its properties based on information that it's fed into this looping system externally. So we have two things external. We have the Perlin noise field that allows us to change the number of petals, and we also have this list of random positions that it's taking our scatter flower. It's taking our splatter circular flower, which is positioned in the center, and then with this pixel processor, we're going to move it around into this space. Okay, so these are the examples. Let me go ahead and start from scratch. Okay, so I will be taking this gradient, and it's a cone gradient. So I mean, in this case, it's a polygon, but initially I started um, with a simple shape node, and I selected from the list that node allows us to choose from. I selected the cone. The reason for using a polygon here is because I found this effect interesting. So the polygon has this curve parameter. So initially this is a hexagon, and then you can just play with this, and I just liked this effect. Okay, but let me delete this one and gradient, sorry, shape, and we can choose a cone. And what we're going to do inside the pixel processor, we're going to create this kind of functionality. So let me bring in the histogram select, and we're not going to fully make the entire histogram select. We're just going to mimic a small portion of its functionality. What we're going to mimic is we're going to have the contrast set to 1. The range is going to be a parameter that we can control, so we're going to call this parameter thickness, and this parameter is going to be position. So we're going to create a histogram select that only has these two parameters, and we will be able to play with the thickness of the ring, and then also change its radius, so to speak. But this is actually where it's sampling the gradient from. Okay, so pixel processor, make it grayscale, go inside. We need to get the position variable, so it's a get float 2, and then from here we need to choose the position, and in order to bring the gradient inside the pixel processor, we need to sample and set this as an output. So sample grayscale, because the image itself, it's a grayscale. And then here, if we would have multiple images, then this list is going to have multiple input images, but image input 0, it's this one. So you can see image input 0. Okay, good. Now let's select the ring. So for this, we will be creating two floats. This is going to be our position parameter, and this is going to be our thickness parameter. And we want to do an addition here. So this plus this, and then a subtraction here. Okay, so those are some values that are around the center value 0.5. This is a bit larger than 0.5. This is a bit lower than 0.5. And we're going to say if the brightness of the pixels in this image here are going to be both brighter, um, I mean, if the pixels here are going to be bounded, the brightness of the pixels here are going to be bounded between these values here, then we want to make those pixels fully white and everything else will be zero. Okay, so let us do this. We will be saying if this is lower than this, then make everything white. So let me actually show you how this thing looks. Okay, so all the pixels that are lower than this value here are white, everything else is black. Then let me do the opposite of this. So greater, all the pixels from here that are greater than this, make them white. So it's this. And now we want to say, hey, what about the pixels that met both these conditions? So we can say like, hey, and the pixel respects this and this condition. Okay, so this and this, and if we put this here, now we got a ring. This is maybe it's kind of the intersection of those two rules, or maybe like those two rules combined. And then if we play with this thing here, this is like the position parameter in our histogram select, and this is like the width. Okay, good. So the thing with the while loop node is that it requires a kind of a template um, for you to construct in your mind and follow that template all the time, and this will help you to just know how to start and identify what you want to do. So let me create the template first. What we have here is we have a procedural system that has two parameters already, right? So we have these parameters, the position and the thickness. Uh, they're currently constant values. It's something that we hard coded here, but we will going to be changing this from a constant to something that changes in time. Okay, and I really like to, for all my procedural systems or for all my templates, I like to frame in red the things that I want to change in time. So these are going to be variables. Okay, and I'm going to also put this thing in a larger frame and say this is my procedural system. Okay, and it is important to pay attention here. This making of the template, it's really important. So first of all, we started with our procedural system. We defined that the things that are currently constants, but we want to change them. Okay, so now let's build the loop infrastructure and the rest of the template. So the while loop node is going to be put in here, and it expects three things to happen, and it has this init input, it has the exit condition, and it has the loop body. This is going to be the loop body. It's going to be fed in here. The exit condition, it's going to be a statement that when it becomes true, the loop stops. And then here into init, we need to define and we need to set and declare a few variables. Okay, so let me put for ourselves another frame and say variable initialization. So, and here you would have as many variables as you want, but I would say you can do quite a lot with a number of with a limited number of few variables, and I usually or very frequently use just 3 variables. So these variables are I, and those are names that you can come up with. Just make sure that the names are meaning uh, something that makes sense to you. And in order to set a variable or to assign it to something, you're going to use the set node. And this is going to be named I. And if you've done loops before, you'll be familiar with the I and I++. And maybe I think I stands for iteration or iteration number. Okay. I also do another one which I like to call n, and this is how many times I want to, not to, but n. This is how many times I want the loop to iterate. I will be putting 64 for now. And lastly, I need another variable that it's going to be called luminosity. Again, this can be named anything, but I was inspired by the naming that is in the fxmap node. So this is going in this variable here. We're going to accumulate all the pixels and all their brightnesses and things like that. So that's why it's called luminosity. Okay, good. Now we have 3 variables, but we only have one input here. So how do we do this? Because we can't connect all of them together. So for this, we have, in order to connect everything together, we have the sequence node. And the sequence node, it's like the semicolon character in coding. So at the end of every line of code, you would put a semicolon, and that would indicate that the line of code has ended and you're ready to move to the second one. So this is like the first line of code, this is the second line of code, this is the third line of code. Okay, so we chain them together with sequences. So 1, 2, 3, and then we're ready to plug this thing here. Okay, good. Now we need to move to the next part of the template. So we had variable initialization. Now we need to move to the next part, which is the exit condition. And what we really do with loops is we're going to do a bunch of computation with our loop body, but also we will use I as a variable that keeps track of how many times we iterated. So we will be taking this I and increase it by 1 every time this entire loop iterates. Okay, and the exit condition is going to be when this value of I became equal or greater than n. Okay, so I will be doing this get float I, and if I it's greater or equal than n, then this statement here or this comparison here becomes true, and then the loop it's going to stop. Okay, so do this. This is like exit condition. And lastly, we need to plug in the loop body. Okay, and we need to do another thing to our template. So we have our procedural system, we have our variable initialization, we have the exit condition, and we also need to do update variable. So, and I'm going to put this one in red. Okay, and in this part, we're going to update our variables, which are I and luminosity. And we're going to let N alone. So this is going to say here, it's going to be our control where we're going to say how many times do we want to iterate. And basically this is going to be the number of rings that we have. But here we need to update I, and we also need to update luminosity. So first let me get I, get float I, and we want to add to it because we want to increase it. So I, it's 0 right now, but we want to add 1 to it. And so this and this, and then set. This construction here is important. So you're taking a variable, get float I, you do something to it, and in order to update it, you set it again. So get, do whatever computation you want in between, and then set. Okay, good. So we updated I, and then we also need to update luminosity. So let me do this as well. Get float, going to take luminosity. It's already here. We can add, but we can also do a max. And max is like the maximum blending mode. So it's the same as this blending mode here, like max. It's going to be showing the brightest between the overlapping pixels. Okay, so here luminosity, it's going to be max. With this, and also set luminosity. Okay, so we had our get and set that allows us to update luminosity. And we're almost there. We need to plug these things here. So in order to plug them in this one, we also need to use the sequence node. Okay, so we first update I, and then we update luminosity, and now they are connected together. Okay, so I think we can go ahead and set this thing as an output. And we also want to preview the pixel processor. So the loop actually has executed, but we are not able to see anything going on yet. And that's totally fine because we need to go in here and replace these constant values with something that changes in time. And what changes in time? Well, the fact that we use I, and I now it's updating with every iteration. So now I starts from 0 and then goes 1, 2, 3, 4, 5 until 64. And I also want to make sure that I point this thing to you. So even though I said here that the number of iteration is going to be 64 and my exit condition is set like that, you need to make sure that one more thing allows you to do this. By default, in order to not get stuck in an infinite loop, the node itself, it's set to max iteration to 32. So no matter what I do here and no matter my exit condition, this is going to overwrite everything. For safety reasons, it's going to execute just 32. Now that I have an exit condition of my own, I can just go to this one and increase it arbitrarily. I can put, for example, 1000. Okay, so it still have a safe value. If anything goes wrong after 1000 iterations, this is going to stop as well. Okay, good. Now I want to replace this value here with something that changes in time. If I move this, you can see that our ring, it's changing its radius. I like to do this kind of thing. So on this wire, I want to put a dot like this and then connect this thing here. So this allows me to plug something on this wire. I'm going to get I, so get float I, and then if I plug this thing here, it's going to do something interesting. We're only seeing this dot, and this is because these values are really large, but I can multiply this by something small. So okay, so if I multiply this by 0.02, now you can see we have this these concentric circles. Let me also do this maybe for this time 32. And then let me, instead of doing this, I want to do something else. I want to have no matter how many of these rings I have, I want to have a full circle filled with concentric rings, not like a larger hole here in the middle, okay? So for this, I need to take I, which is from 0 to 32. I need to divide it by n. Something like this, okay? So now I can plug this thing here instead. Okay, so now if I go here and change the number of rings, you can see that I always have the full thing going on. I also want to decrease the width of the rings, maybe put like a 2.5. Okay, good. So we have this thing going on, which is already interesting and we're happy with it, but we want to add a bit more things to the system to make it more interesting, okay? So this created a number of dynamic rings for us that we can change. Maybe do 48. And we also want to move things around. So if I add something here, and then I float 2, this allows me to move things around, but you see that everything is moving. But I don't want to move the entire thing. I only want to move each ring individually, and this movement should be based on every iteration. So we already can do this, and let me take this. I divided by n once more and put this thing here. Okay, so it doesn't work, and the reason for it doesn't working is because this is a float value and this is a vector float too, and this allows me to move left and right, and this allows me to move up and down. I only want to move left to right. This is a float too. This is just a float I need to make. From this float I need to make a vector float too. So vec float 2, plug this into X because I want to move horizontally, put a 0 into Y because I don't want to move vertically, and then replace this thing here. So, okay, now we're getting this effect, which I think it's interesting. So we moved things individually. So now every ring it's moved individually based on the iteration number. Maybe it's too much. In order to have a control over how much we move, we can multiply. So if you multiply by 0, then it's doing nothing. But then you can multiply like this. So now it's like a cone that it's pointing in a certain direction. Okay, good. So that's also interesting and I like it. And let's say that what if we want to move it gradually, and first it moves in this direction and then it moves in the opposite direction? So let me do it like this. Maybe if I put a minus 0.5, then it moves in this direction. Okay, but I can do something more, and I want it to start here and then go here and then return back to this thing. Okay, so let me do this. This is from 0 to 1. I will multiply this by pi because what I want to do, this starts at 0 and then ends up with 1, but I want to make this range starts from 0, be 1 in the middle, and then return again to 0. So if you imagine starting from 0 to 1 is like 0, it's here, and then it moves to 1. But then if I make it to go from 0 to 1 and then back to 0, I can make it that like an inverse curve. So it starts at 0, then it goes like this to 1, and then returns back to 0. So I'm going to do this. And in order to make this range do that, I need to take this thing and multiply it by pi. And then do a sine. So now this is starting at 0 and then goes to 1 and then it goes back to 0. Okay, and I also want to blend between these values, so I will be using a linear interpolation. So I want to transition between minus 0.4 and 0.4. So let me do a linear interpolation based on this, and then I also use a negate. So this is minus 0.4, this is 0.4, and then we do this and this, and then put this thing here. So now we're getting this interesting effect. Also, we can do even more things to it. It's already looking interesting. To create that looping animation effect, we should add something here after the sine, not after the sine, before the sine. So here we need to add something, maybe like 5. Okay, and then once we change this, we're getting this looping effect. Okay, maybe this is a bit much, something like this. Okay, So I think it's doing like an interesting wavy effect. And that's already interesting, but we can do one more thing with this. This again, it's between 0 and 1, and all our rings are currently with the brightness 1, but we can multiply them by this changing value. So multiply. Now, if you multiply by 0, they all disappeared, and then we can just take this sine wave and put it back. Okay, so now when I change this value here, okay, so the effect is interesting, but I don't like the fact that they are disappearing altogether. So the reason for this is because this is strictly between 0 and 1. We can put this into a linear interpolation like we had here. So we can put a lerp and not here. We want this thing in here, and we want to put two values, float 0 and maybe between 1 and 0.2, so it doesn't completely disappear. Okay, maybe even more. And one more thing which I realized is because sine goes from -1 to 1. And in this case, it was correct. So if I put this thing in here, that's correct. That still remains from 0 to 1. But then if I added this thing here, now our sign actually ranges from -1 to 1. And that's why some of the rings disappear. And then if we want to mitigate that, we can put a -1, 1 to 0, 1 range. Okay. And then maybe we can increase this effect more. Something like this. And now if I change this, then also we have the wave effect and the brightness changing. Okay, good. Now, lastly, what I've done is I just put a gradient map after it like this, and also an FXA color. So what the FXA now does is going to take this very sharp stair step effect pixels here, and it's going to do a very smart blur that it's applied the to the edges. So FX grayscale. So before and after. Good, we have our first example done. The second one is this effect. So let me take a Berlin noise. And then also let me take this quad transform. Let me just do it. Okay, so I want to make it like this. Okay, maybe like so. And then again, I will be using the same idea of using the histogram select, but inside the pixel processor. So bring the image inside. And I could be going inside this one and copy this part, but I don't want to because repetition is good. So we're going to build it from scratch again. So what we want float that it's going to be our position parameter, and then this is going to be our thickness, and then we want to add this with this, and we also want to subtract, and then we will say the conditions. So if the brightness of the pixel is lower than this and greater, if the brightness of the pixel is greater than this, and if those both conditions are met at the same time, so and if this and this, if this and this are true, then make the pixels white. So boolean to float. And now we have this. Great. So if we change this position, then we're going to scan through the values of the Perlin noise. Okay. Now great. Again, let's do our template trick. So this gets into our memory. Okay. This is the things that we want to change. This is our procedural system. Here is going to be our while loop. Okay, and then we have the variable initialization. So and if you remember the variables, that will be totally amazing because we're going to use the same variables. So this one is I, this one will be N, and the last one will be luminosity. I'm going to shortcut as LUM. We need to sequence things together. And we're done with our variable initialization. Right, now we need to do our exit condition. So get float I, and we want to stop if I is greater or equal than N. So greater or equal. When this becomes true, then stop. We also want to go here, and now that we have this thing going on, so N should be maybe 64. And then we want to go in here and extend this. Now this was our exit. We have lastly the update parameters, the parameters, or not parameters, sorry, update variables. The variables that we want to update are I and LUM. So get float I. We want to do something to I, so add. Okay, and then we add 1, and now we want to update it, so set I. Good. And we also want to update the luminosity, so get float LUM. We want to put a max here. And then set LUM. And then these are our updates. chain them together with the sequence node. We should also put the frame as well. So update variables and then plug this thing here, set as an output. Now, great. We have this thing going on. We know that we want to change some of these parameters, but also let's think what happens with if we do something else. So maybe what if we start and add here what's happening? So float 2. Well, if I move this, is going to move left and right. And if I change this, is going to move up and down. So I'm thinking we can make something that looks kind of a bit like a 3D printing. So layer by layer, we're going to move these things up, okay? So instead of doing this with a constant, we need to do this with a variable. Okay, and we can take our I divided by n. So I divided by n and see what's happening. And now that I know I want to move vertically and not horizontally, so remember this is a float and we want to change it. So I mean, we want to put it into a vector, but we also want to put it here into the y component because this is the part that it's moving up and down. Okay, so we should put this here. And we don't want to do anything horizontally. So now our vector, it's like this. Okay, great. Now it's interesting, but maybe it's too much. Let's multiply this by a small number. Okay, not 0. So maybe 0.3. And this acts like the height of our extruded, maybe like 0.5. Okay, so that's one thing that it's already interesting, but we can do more, of course. And we want to also change this value. Remember, this value, it's our lines, our scanning of the Perlin noise. So maybe we want to start from 0 and then go to 1 and see what's happening if we do this, or what happens if we do this. So replace this with something that changes in time. Well, we can do I divided by n and plug this thing here. And now we got this result, which I think looks interesting. Okay, so now you can go ahead and play with this disorder. So now everything changes. Okay, the effect, it's looking interesting. We can do a bit more than that. So let me actually do this. We also want to put, instead of having this simple transition from 0 to 1, we can put a curve node. So that allows us to do our own transition. So now this is going from 0 to 1, but we can make it from 0 to 1 to 0, and then maybe to something like that. We can do something crazy, okay? So we want to read values from this. So I divided by n is just a gradient that was I divided by n is just a gradient like this, where it starts from 0 and linearly increase to 1, but we can change that. So plug this thing here in, and now we have this thing here. We want to put it into a vector, so we can sample that sample grayscale image input one. This is our gradient. We can't put this thing here because this is a vector, and this is just a float, so this requires a vector. And vector, so this and this is going to iterate and loop and read values from this texture. So this loop is going to go here and read values from here, from here, from here, from here, from here, and then based on these values is going to change the position or of our histogram select, so to speak, right? So let me preview this and then do this. Okay, so now things have changed, and I think the reason for this is because it would be good not to start from absolute zero. Okay, and then something like this. So it's already another interesting effect, and then you can change it like so. So maybe try and do this. What happens if I do this and this? What happens if I do this and this and this? So I like it when they connect together like this, where they kind of create this tunnel here. Also, let me do one more thing. I'm going to need another gradient. I will need to rotate this one 180 degrees, and I will duplicate the quad transform and apply the same transformation to this one. I don't like these things here. These are probably because the sampling is bilinear. Do it to nearest, then they're gone. Okay, this is our pixel processor node. I want to plug this thing here. Okay, I'm doing a bit of graph arrangement, not too much though. Okay, great. Now I want to add a bit of depth to this drawing. So for this, I want to bring inside our new gradient image. So sample image 2, and these are the coordinates that take the image and lift it up. So we need to apply the same transformation to this one as well. So then our gradient, it moves up layer with layer by layer, and then those are these lines are fully white, but we can multiply them by that incoming gradient, and that's going to give us the depth effect. Okay, so you can see how whatever is closer to us is white, and whatever goes uh, away from us, so to speak, it's going to be darker. Okay. Depending on if you like it or not, so I think I like how it looks right now. We can add one more effect. So the ones that are we can kind of color them by the number of iterations. So some of them go up and down, and we can color them by yeah, by the number of iteration, which might not be. So initially I wanted to say like it's going to be 0 at the bottom and the ones that are the top are going to be white, but this might not be the case all the time. So in order to do so, we need to multiply this again by 1 divided by n. And there's, you can see how I computed 1 divided by n a few times. That's not absolutely necessary. It's just like not to make a total mess out of the code. This is totally fine if you do this. So you can take this 1 divided by n that we just computed and then put it here. So this can be removed, and then this can be a bit. So, and maybe if every wire is too messy, you can do this. So again, because I have 1 divided by n computed already, I can multiply it here. So multiply, and 1 divided by n, it's here as well. So okay, so now you can see these ones at the bottom are darker and the ones at the top are lighter. Yeah, so maybe this is interesting as well. Okay, so now you can play with this and change what happens. Oh, this is interesting. And then also changing the disorder gives you like different effects. Okay, so you can go in here if you want, decrease or increase the number of lines, can give interesting results. Maybe 128 looks good. And if you want, you can put a gradient and an FXA at the end, something like that. Okay, let's move on to the next effect. Okay, right. So I will duplicate this setup here. I mean, should I do it from scratch? Yeah, let me do it from scratch. So this is something that the thing that we want to achieve, but I will be doing it like this. So splatter circular grayscale. Okay, we want the pattern, we want it to be a disk. Pattern number. Pattern amount to be 3 in this case. Luminosity by pattern number. Okay. Then I will be putting a histogram scan. Then a distance. Increase it all the way. I also want to remove the tiling. Put an auto levels after this. Blur it. The intensity of 10, I think it's okay. And lastly, I want to invert. something like this. Okay, so delete this one, rebuild it from scratch. Then I think I will put a normal after this. So normal, and then bring it an FX map, make it grayscale. So I need to, for this one, I need to replicate this functionality where we have a pin that we can move around. So this is where our marble is starting. This is the starting position and it goes down all the way to the bottom of the, let's say, the ball that has like a 3-hole bottom or something like that. Okay, good. So double click in order to make this pin, double click here on this graph. And here into parameters, I'm going to make a new one. It needs to be a float 2. It needs to be a position, and then it needs to be have a name. I will be saying origin 2. Great. I will be plugging this thing here. Go inside. The blending mode will be set to maximum. The pattern will be a disk. The pattern size will be something small, 0.005. Okay. Then I will be doing a branch offset. So the FX map considers 0, 0 to be here, but we're going to change that and we're going to make the 0, 0 to be here. So in order to do this, we will go into branch offset minus 0.5 and minus 0.5. So now we have it. Then we need to iterate this. So we're going to iterate maybe 256 times. So integer 256. Okay, and also I want to get the origin that we made, so origin 2, and I want to set it to a different thing, so set, and I'm going to set it to O2, and this is necessary, so it's going to access the position of the pin that we created. But then in order, because we want to update it, in order to be able to update it, we need to take it, and this is going to be the initial state, and then we want to cast it into something else, and this variable it's going to be updated. So otherwise I think it will not work. Okay, so we have this and this. I think we should be able to chain things together. Now we are in the FX map node here into the iterate node. The thing that the iterate node expects as an output is an integer, so expected output type is integer. This is an integer, this is a float too. So we can chain a bunch of variables and computations together and chain them with sequence node, but the last thing that we connect to the sequence node should be this integer, and this is going to tell the iterate node how many times it's going to loop. Set this one as an output, set this one as a root. Okay, currently nothing really happened, but it executed 256 times, so we currently have 256 dots on top of each other. Now we're going here into luminosity, we're going to get float 2, and the variable that we want to update is O2. And then at this variable, we want to sample the normal map. So for example, at this position, the normal map is going to provide us with the vector which has a direction, and that direction is going to tell us where to move next, and we're going to repeat this a bunch of times, and this dot is going to travel along the way from light values to dark values, from the high regions of the ball to the bottom of the ball, so to speak. Okay, so we only want x and y from the normal, so swizzle float 2, but we also want to change the normal information to range from 0 1. It needs to range from 0 1 to minus 1 1. So in doing so, we need to multiply. It's a scalar multiplication by 2. So now range is from 0 to 2, but then we also want to subtract from it a float 2. So this minus 1. Okay, so now this is between minus 1 and 1. And okay, so we got our origin. We sampled the normal vector at that location, that's fine. Then we want to add this to this. So we're taking O2, we're doing something to it, and then we redefine it. So set, and it's again that thing which is get, do something, and set. This is the update of the variable. So we computed the position, but we are in the luminosity channel. So the last thing that we need to output is either a float or a float 4. A float is just a luminosity, a float 4 is a color. This is a position, it's a float 2. We can't set this one as an output. So no worries for that. Sequence, and then all our dots are going to be white, so float 1 white. Okay, set this thing as an output. Again, nothing yet happened, but we're almost there. We just need to go here and into the actual channel that does, or that has to do with the movement, which is pattern offset. We're going to get float 2, and we're going to call in or bring in the variable that we just computed, which is O2, and send an output. Okay, so it seems to be working, and then let me actually test it out. So preview, and then okay, so it seems to be working. We're starting here and we're going down the road. Let us also preview what's going on. So maybe a level, decrease this, and do this. So again, as you can see, if we're starting here, we're going somewhere. We're eventually arriving at the bottom of the ball, okay? But this is like a direct thing. So for example, a marble, if you drop it or if you let it slide into a ball, it's not going to go directly here. It's going to have some inertia, and it's going to start here and is going to go here, but it's also going to overshoot and then maybe go here and then return as it loses energy, and then do a bunch of do until it settles in at the very bottom. Okay, so this is not happening right now, but we're going to make it happen. Okay, so what I'm going to do is like by no means at all physically accurate or anything like that. It's also not a super complicated thing to do. uh, Making this kind of simulation more accurate, it's something that is fairly common thing to do, and is not like really tremendously complicated, at least like the basic implementation. So what's happening is that we're currently only updating using velocity, and that's why we don't have any inertia but we can do something else. So we can integrate twice. And instead of integrating from velocity, we can integrate from acceleration. And this is like the force equals mass times acceleration thing. Okay, don't need to go into detail too much. I'm not an expert myself. I think I've done this kind of simulations a few times, but never really sat down and really dig into it to understand it. Okay, so let us update the simulation to have a bit more of a robust behavior. Okay, so currently this is serving as velocity, but we don't want that. We want this to be acceleration. If you if you might be familiar with velocity is the first derivative of position and acceleration is the second derivative of position, we're going to do this kind of thing here. So we need a float too. We don't have a velocity, but we want to create one. So for this, I'm making a empty, I'm going to initialize with 0 this vector. So set, and I'm going to call it VAL, short for velocity. Okay, so now we have this variable that we can also update. So go back here into luminosity, and here we're going to do this. So this is acceleration. We're going to get flow to VEL. We need to add something to it. We need to set it. And then we need to plug this thing here. Okay, so it seems that it does something for us, but maybe it's a bit too strong. So you can see the distance between points, it's very, very large. Let me have a look at it, just not to waste too much time to remember how I've done it. Okay, so here it seems like I just put a damping factor for the velocity. So this is making sure that the velocity kind of, this is how I'm simulating the loss of energy, and this is maybe like friction or something else. So I'm damping the energy of the velocity with time. This means that with every iteration, the velocity loses like around maybe, I think it was like 3% or something of its force. And along many iterations, then the velocity becomes really, really, really small. Okay. So go in here, here, and maybe after this put like a scalar multiplication and load. And this is like 0.98. Okay, let me check another thing because it still seems to be very powerful. Oh, also here I just decreased the strength of the normal itself. So I need to do this thing here. I can do this either here or I can do this inside of the FX map. Actually, for the sake of consistency, let's do it inside the FX map. So going here inside the luminosity, after this step, I can also multiply again. So now I'm decreasing the scale of the magnitude of the acceleration vector. And I think it was like 0.08. Okay. So maybe it's like this, and I'm hoping if I change things, okay, I'm seeing some spiral thing going on at some times. Okay, just want to make sure that I'm using similar values because this can be sensitive. So I'm looking here, it was 0.97, and here I think I'm 0.98, 0.97, maybe like this. I'm just intrigued of why sometimes I get like really um, sharp lines. I think maybe the blur here might be stronger. So blur, intensity is 10, invert grayscale. I mean, I should be looking into this one. So blur it was 16 instead of 10. So let me get back here. Blur, it's 16. Yeah, it's a bit more rounder. And if I go here and now change this, yeah, I still don't like how I get this effect here. Maybe let me try and change this one. So if I bring this one here, yeah, this seems to be more different. Intensity 0.08. Intensity 1. It might be this. I think this might need to be a bilinear thing. That's not like terribly crucial, but still wanted to have a similar thing going on. So it might also have to do with this particular setup. I think this also matter because I don't have the same thing going on. So this is my splatter circular in my initial case, and my splatter circular here, it's more like so. Maybe that matters as well, so I can change it. Yeah, so definitely it made a difference, so it's not anymore like a straight line. Okay, good. So now if I change this, this ends up in like different places based on the starting point. Okay, so we only simulated one, but we want to simulate like all possible starting positions, right? So we can do this, but we can do the same thing, but inside the pixel processor. Okay, so we're not going to visualize the path itself, but we're going to color each pixel itself to with the color where it ends up with. So the pixel is going to travel and is going to land on whatever spot it likes, and then whatever the color is at the end where the travel has ended, then the pixel is going to be colored with that color. Okay, so for this I will be taking this one, and instead of making 3, we're going to make 5, pattern amount 5. Okay, and then we're going to maybe take the same thing like here, also do the normal. Okay, so now inside the pixel processor, we are going to do the simulation for every single pixel. So we need to get the position, and we'll be naming this. We're going to make this like set and initial position. I mean, we can call this like starting point. Okay. And then we can do this like a well, not a sequence, but I think maybe we can go directly to the while loop. The setup for this, I think it's going to be even more simple. We only have this variable that we want to update. The exit condition is going to be controlled by this. We need to do the body of the loop, so get float to we have starting point, and we want to sample the normal map at the starting point. Maybe make this like 0.08 or something. I mean, I would leave it this by default. I think here I used 1, but it seems like I blurred it a bit. So I blurred the normal map with a strength of 4. Okay. Then go inside. I want to take the normals and change them from the range of 0, 1 to the range of -1 to 1. So I need the X and Y. I need to scale them with the value of 2, but then I want to subtract 1 from them. Okay. I also think I need to create a velocity vector here as well. Let me check. So here in the pixel processor, yes, I also have a velocity vector. So I am here. Okay, great. So we want to update things together. So we have our declaration of variables. We for each position, we extracted the normal map, but then we want to update the position. But we want to update the velocity first and then the position. So get float, and we get the velocity. So we need to add. We also need to multiply it by something that's decreasing over time. So velocity is going to all the time decrease. Something like this, and then set. Okay, and lastly, we want to update our position. So that's our acceleration. This is our velocity. Okay, and this is our position update. So we took the position, we've done a bunch of things to it, and then we set it. So I want to copy this thing, starting point, put it here, starting point, then set this as an output. And then I want to bring in this map here that has all those grayscale values. These are the endpoints, or the bottoms of the bowl are colored with these different grayscale values. So here I just sample those, sample grayscale and image 0, set as an output, and this is what we got. Okay, so let me think for a while. Let me check a few settings from here as well. So this was 0.96 and this was bilinear. This was also bilinear. Let me check. So bilinear is good. 0.96, it's also good. This also should be bilinear. How many iterations did this thing had? 128 iterations. Let me do the same here. This has only 32, so 128. Okay, so now we're getting something similar. So we've done, and also look, it's really fast to do. And we've done this kind of simulation. So we started somewhere and we let the particles slide into this ball and it ended up somewhere like this. And we've done the same simulation for every possible starting point. And this shows us if I start here, for example, if I start here, this is going to tell me where it lands. Make it maybe I can do something else. Instead of this, I can put a gradient map. I already have one here, so I can use this one. Okay. And then instead of making this grayscale, I can make it color. Instead of this, I can do this. So I'm plugging colors inside. And instead of sampling grayscale, I can sample color. So sample color, image input 1, bilinear, set it as an output. Okay. So now all the colors, all the pixels that are colored, the color represents the starting point and where the uh, uh, based on the starting position, it's going to tell us where the simulation ended. And I think it's pretty cool to make patterns like this. It's a really interesting idea. Okay, great. Now, up to this point, we made loops inside the pixel processor and inside the FX map node. And there are a few differences that I want to make. So the FX map node allows you to um, take an input pattern, let's say like a circle, and it allows you to change its position, change its scale, change its orientation and luminosity. Um, and you can do quite a lot with these things together, but only allows changing of position, scale, orientation, and luminosity. The pixel processor node allows you to do the same, but also allows you to access every it gives you like pixel level access. So not only you can take in things and move them around up and down and things like that, scale them, rotate them, distort them, or whatever, but also you can do this kind of stuff where we had an input image and we really processed it. So we extracted from this image, we extracted that contour lines and we were able to take them and move them up and down. We were able to change their brightness and luminosity and things like that. So pixel processor has this extra a level that allows you to have controls for each individual pixel, while the FX map doesn't, or at least not is not a straightforward thing to do. Okay, good. So we have a few interesting other procedures that we can make. So let me do this. We're having a disk here, right? Okay, so we can take this disk and we can create kind of like an action and repeat the same action multiple times. And for this, this allows us to encapsulate already existing nodes in a functioning, or like in an infrastructure of nodes that can behave like looping behavior. Okay, and let me do this first. So what I want to do is I want to make an action. So take the transform node, for example, and with the transform node selected, I'm going to right click and say create graph from input selection. Now I already have created a few things I want, or I like to name this uh, instance graphs or subgraphs, or however you want to name it. I think instance graph is more correct. I like to name the iteration. So for example, I have 1, 2, 3, 4 already. I'm going to name this iteration 5. Okay. Now this thing has been created. I'm going to drag and drop it. So it has the transform node inside of it. I'm going to hit Control plus E to go inside. We need to input a grayscale and also output. So we chained, or we put our action in between an input and an output. Now our node is having input and output. If we plug things here, then we get that. Okay, so then what we can do with this? Well, we can go inside and then take the transform node and just shift it to a bit. And that was our initial dot, which is not moved, and then this iteration 5 node has performed this action of movement. So now I can duplicate this, and now it keeps moving. I can take these two together and now duplicate them and chain them together, and I can do this once more and change things together. So now we iterated, or we applied the same function 8 times. Okay, so we started here and we moved the circle a bit every time. Okay, and it's cool because if I go inside now and change things, then everything else changes. Okay, so all the other nodes are going to be uh, simultaneously modified by the same action that I'm doing here. Which I think is great. So now we have this, but I think we can also do a bit more with it. What happens if this is my moving action, right? But then I can take and put a blend node and take the original input and combine it with the moved one. Okay, so put like a max and then chain things together and then look at the output. Well, all of a sudden you can see we have a chain of dots together. Now, what else can we do? I think we can make like a trail effect. So, for example, where we can uh, have the latest or the more recent dot be the brightest and have all the past dots to be darker. So for this I can for example switch these connections together, and I can just go and decrease this I can decrease the opacity here. Or maybe I can put a levels node and just decrease the brightness. Something like this, it's even better, right? So it's applying the levels to all the nodes in the past, to all the dots in the past. Okay. And then you can also do this if you want. Now you have a bunch of colored dots. So that's interesting, but you can do even more. You can take the transform node and you can scale them, for example, inside or outside. And then even if I rotate it, now it's creating a spiral. Okay. And I can do even more. So now I have 8, but I can just take all the 8 that I already have and plug this in here. And now I have more. Okay, good. So this effect was interesting and it's a very similar effect to this one. We'll be creating a similar effect, but in this one we're going to also add a blur and we're going to have more iterations. Okay, so I am going to start again with the same setup, disk that it's moved to the left, and then also let me have a look inside here. So what we are doing is we are blurring uh, the input, and we also take it and move it and we combine these things together, and let's see what happens over time. So again, I will be taking a transform node, set this one, create a graph selection from it. This is going to be iteration 6. Okay, we need to do input, grayscale, and output. Okay, and then what we want to do is we want to move it, but also we want to blur things. Okay, so we have this, then we want to blend. We're going to be doing a maximum blending mode again, and then just a blur node. So maybe not this one, like a blur high quality. And then I will be moving the dot just a tiny bit. Okay, good. So now we will be repeating this action many times. So duplicate. And I want to also show you how fast the graph actually increases. So I take everything and duplicate it every time. So the graph grows exponentially. So it's not really too much work to do. So all of a sudden I have 64 duplications. Okay, good. Now let's do something else. Let's decrease the scale of the dot and also rotate. So now we're getting this spiral kind of thing. I want to go here into the tiling mode and no tiling. Okay, now this is giving me this kind of spiral effect. Also, I think maybe the blur it's too much. We can play with it and have it a bit more sharp. So you can see how the dot gets blurred and more diffused over time. Okay. And also if you want, you can do this at the end. Just color everything based on how you want. And again, you can go inside and add more instructions or information or change things, or go here with the blend node and play with the opacity and things like that. So pretty interesting thing to do, I believe. Okay, next one, let me see what this one does. Okay, this was um the weird one, so to speak. Let me do this, duplicate. And I think for this example it's more important just um, to introduce or to show that we can introduce this setup here where we can keep track of the number of iterations, and based on the number of the iteration we can do some extra or we can have some extra or more control. Okay, so I'm going to, I mean, I think this one was a bit more interesting. So how it was? Well, I had one input that I didn't want to change. This is the thing that I want to change. Okay, so I need first of all use a transfer node. I mean, just for now I will be doing this. Create graph from selection. I think this should be like what iteration? Iteration 7. So again, okay. So we want to do a get float, not get float, sorry, an input grayscale, and we want to straight output it. And this will allow us to just take an input image like the disk and don't do anything to it directly yet. Then we want to do another input grayscale, and we're going to do something to this one. So this is going to be a transform to the something like that, and then also output. Okay, and then we also want an input value, and then we want to do a value processor. Then we want to do this thing here, get float. It's called the input, so this is called input. You can name it how you want, let's say like I. So now this thing it's called I. Okay, so then we want to update this, so add float, and we're going to add 1, set as an output. So it was 0, now it's 1, and now we also want to output this as well. Okay, so our node now has 3 inputs and 3 outputs. The input, the first thing that we get is this. Okay. So now this is the part that I think we should also plug this thing in here as well. So what I want to do is I want to move the dot to the left, but also move it up and down sometimes. And I'm going to alternate between the dots that I move up and down based on the number of the iterations. So for example, if the number of iteration is odd, then move up, and then if it's even, move down, or something like that, or vice versa. Doesn't matter too much. Okay. So good. Well, currently we want to just do this action where we move to the left, and then if we do this, and this, we should see the dot moving. Okay, so it's moving, that's good. But we also want to make the change, so we want to add the dots together. So this action should also contain the blending. So blend, where we accumulate the actions together. So maybe this is the past, this is the current state. We add them together, or maybe use the max node and put this thing here. Okay, so now we have 3 dots. That's good. And let me make sure that I'm doing the same thing here, because I'm not sure. Okay, so it has been a movement, and then also I'm doing this. Okay. So I want to take this and move it up. So transform and move it up. And then I'm going to use the blend node. And this is the original, this is the moved one. The blend mode is going to be switch. I want to be in this one. So the blend mode is switch. I need to go here, create an input value, put this 0 here, and into the opacity, I'm going to get that value, and we're going to say that value is going to increase by 1 all the time. And then we're going to take the modulo 2 out of it. So mod, if this is going to be 1 2 0 1 2 3 4, this is going to be 0 1 0 1 0 1. So every even or every odd number is going to be turned into either a 0 or 1. So this is the mod 2 function. And the reason for doing this is because the blend mode with the if the blend node has the mode switch selected, then it's going to execute either one either of one of the inputs based on this based on the selection that's coming from the opacity channel. So this is going to be either 0 or 1, and this is how the switch mode works in the blend node. And it's basically going to execute either a branch or the other, or it's going to execute either the foreground or the background based on the opacity values, which is going to be either 0 or 1. So if this is 1, it's going to execute this. If it's going to be 0, it's going to execute this. Okay, so set as an output. Okay, and then I think let me check again, not this but this. Let me remember how I connected things here. So I have the switch, And I have a new blend node here as well. Okay, so I think it's like this and like this. Yeah. So now this is alternating. It's doing every other one. It's moving it up. Okay, so this is another interesting way to do things, and now you're making some decisions based on the number of the iteration itself. You can also, this is the part where we move things up. You can also add a blur here, so maybe blur grayscale. So now the things that are at the top are blurred and the things that are at the bottom are not blurred. Okay, so you can continue doing this. Okay, great. Now let's move to the next one. This next one is pretty interesting. You can make fractals with it. I think I made a video tutorial before about this, but we can have it once more. So I'm having a simple shape that I went into the size and reduced its x and y amount, and then took a transform node and moved it down. Okay. So I will be using another transform node, and I think I will be creating a new iterate 8, iteration 8. We need again input grayscale, output grayscale. Okay, so currently it does nothing, and we take whatever it's coming in, we can scale it. I will be deactivating the tiling. I'm going to use the blend node, add them together, take this one, position it like this. That's great. And I also want to take this. Okay, reposition it like so. Maybe use another blend node here. So this, and we add them together. So add, then add this. So now I want to put this thing. So just made like an Y shape and then connect this thing here. Okay. So now we have it like so, but then if we duplicate and we chain these actions together, we're going to get a fractal tree. Okay, which I think it's again something interesting, and then you can just go inside and play with this and change how it looks. Okay, This was interesting as well, and I think maybe this is the last one, and we're going to have a bonus as well. So the last example was that we took a splatter circular node and we stuck that inside of a looping system of our own. So let us do this again. We have a splatter circular grayscale. We want to change the pattern to a square. Then go here into the size. Maybe like this. Also decrease the radius like so. Okay. Then we're going to take this and let me remind myself we are iterate 8. You need to make a new one. Create graph from selection. So iteration 9. Okay, and here what do we have? We have an input. We have an input that it's accumulator. We have an input that takes the Berlin noise. We have an input that takes some array of positions. Good. And we also have an input that keeps track of the iteration number. So first of all, let me get, input grayscale and output grayscale. This is going where we're going to accumulate everything, all the graphics. Then input grayscale again. This is going to be where we take in our Perlin noise. And what are the outputs again? So, okay, the Perlin noise also goes like that. Yeah, that's good. So Perlin noise, maybe this, put this into the second input. Now it is here. Output Perlin noise goes there. Okay, then input value, this should be 0. We should output for now again. And lastly, input color. And output color as well. Okay, so then we want to make our list of arrays, our array of positions, sorry. So I'm going to create a random list of positions by using white noise. So, and the size will be 8 pixels by 1. So this is it's going to generate for us a list of 8 positions. So I duplicated this one and I just changed the random seed. I will be using a pixel processor, connect these things together, change the size of the pixel processor to match it. So 8 pixels by 1. Go inside and put everything into a vector. So sample, sample again, bringing bringing both images, put them into X and Y. Now this is a list of positions and then we need to output them. So I will be completing this information here. Okay, so now this is a list of positions which goes here. Okay, now we need to go inside. This is a 2K texture, we need to go and make it match the size, so 8 pixels by 1. Okay, perfect. Now we want to add something here to increase our iteration number. So add, sorry, it's value processor. Bring this in, go inside, get the input, add 1 to it. Put this as an output. That's perfect. So now this is 1. We connect everything. This is 2. Great. Okay, so now what do we want to do? We want another value processor. So, and we will be connecting the Perlin noise, we will be connecting the positions, and we also will be connecting this iteration number. So in this case, because we have only 8 positions, we're going to do just 8 iterations, but we can do more, of course, if we want. So go in here. I want to loop through through all the position in this texture here. So I want to read the positions from here to here to here to here to here to here, one by one. Okay. So in order to do this, I'm going to take the this is the iteration number, so this is this value here, and we need to divide it by 8. Now we need to put this into a vector. Now we need to sample. So now we're marching pixel by pixel into this texture. This is image input 1. Make sure that your image input 1. Okay, we want to extract the position here. So those things are going to be fed into a pixel processor later, but also we want to sample the Perlin noise at these positions. So the Perlin noise goes into 0, and what's going to happen is that this value processor is going to look into this pixel processor, into this Perlin noise at these positions and sample the value from the Perlin noise and send this value to the splatter circular grayscale to inform the number of petals. Okay, so we need to pack this information. So this is our positions. We're going to use this to move our flowers around, and this information is going to inform the number of petals. Okay, so we can pack this information into a float 3, set it as an output. Now it's like this. Okay, so into the splatter circular, which is like this, we want to go into, first of all, create. We need to create a new input parameter. It needs to be float free. We plug this thing here inside, and then we go here where it says pattern amount, into this channel, empty function, get float 3. That's the thing that we just input. We need swizzle float 1, but we need the z component. So in the x and y we had stored the position. In the z channel of the value processor we stored the value from the Perlin noise that we sampled from the Perlin noise. Now this is something that which is between 0 and 1, but a flower has like an integer number or of petals, so we can use a linear interpolation to blend between some values, maybe between 5 petals and maybe 17. And then we also need to cast this to an integer. Set this as an output. Now this has changed. Okay, so the system actually functions. If I change the Perlin noise, you can see how the number of petals changed because this is sampling the iteration. It's sampling the Perlin noise, and then it informs the number of petals. Now we want to do the moving, so we take this, plug it into a pixel processor. So this, okay. So we brought in the flower, and we can move it around based on this information here, based on the X and Y. So we need a float 3 here as well. Sorry, get float 3. That's the input, but we only need the X and Y. So swizzle float 2. And then we want to add, and now the flower actually has moved around. And we're going to do a bit of tweaking, but now the last thing that we want to do is that we need to blend. So this is where we accumulate all the flowers. So here we need to add so this, and it's going to be maximum with this, and then put this thing here, and now we should see 2 flowers. Okay, and then we should see more flowers if we keep connecting things together. More flowers. Okay, now let me do something here. Let's scale this size a bit. So now the flowers are randomly scattered through the entire space, but maybe we can scale things together. Something like this, and then I also want to go in here into the pixel processor itself and maybe add or subtract something to nudge them to the center, more to the center. So I'm going to be minus 0.25 and minus 0.25, something like this. And then take this and duplicate more and connect. Okay, and then see all the flowers and maybe change the random seed. Also, I want to change maybe the brightness. Go into the splatter circular. I think still the size may be too much. Maybe 4, maybe 0.5. Okay, and then also here where it says into the color, we can get float 3 input, and then swizzle, not this one, swizzle, and extract the Z component where we are sampling from the Perlin noise. Okay, so now we're having them colored by the Perlin noise itself. Okay, so it's great because now we actually have a full node that we brought into a looping behavior. So we have a full substance designer node that we integrated in a looping behavior. So you can do this with every node, and you can basically do a lot of crazy interesting setup of nodes here and functionality and make it work, and you just have it stuck inside of a looping structure. Okay, and it will work. So for example, now I can change if I want. I can change. I only have 8 flowers, but I can change this, for example, to 32 if I want. So 5, 5. This should be also 5, and then go in here, and then this one should be 5 as well, and this instead of 8 should be 32. Okay, and then the only thing that I need to do next is increase the number of iterations. So currently it's only 8. Now it will be 16. And now it's going to be 32. And maybe I can make this case a bit more extreme, just to see the maybe just 1 and maybe 64. And also the Berlin noise should be like fully ranging from 0 to 1. Yeah, so definitely wanted to see like really more variation in terms of the number of petals and things like that. Okay, great. So up to this point, we have loops that are inside of pixel processor. We have loops that are inside the FIPS map. We have loops that are inside of instance graphs. We have iterated functions where we repeat the same operation many times. So we repeat the same operation many times and we get fractal-like structures. And the last thing that we want to do is the bonus, and we're going to make the simple blur node. So let me show you which one. So let's take a regular square and do the blur node. And this is like uh, the basic one. I think this is like really old and things like that, but we're going to make this blur node. Okay, so I'm taking this I'm just duplicating this square. I will be making a pixel processor, so pixel processor, take this in, we want to bring in the square. So for this, we want to do a position. And the sample. So now we have it here. Okay, we also want to do shift things around. So for this, I want to move this square up, down, left, and right by exactly 1 pixel. And for this, I need to take this uh, size variable and divide 1 by 8. So this is the entire thing divided by the size. This is going to give us the size of 1 pixel, which is a very small number in this case. So it's 1 divided by 2048. Okay, I will be extracting only this. And then I want to make a vector out of this and add. And I will be zooming in, and what you should be able to see is if I plug this thing here, the square is going to probably move 1 pixel to the left. Yeah, so it did, and it was a significant movement, and this is because I'm really zoomed in. But if I do this again, so it was how it was initially and then how it was right now. So subtle movement, 1 pixel. Okay, so that was to the movement to the left. And then we want to do the movement to the right. So for this, we go to subtract instead. So this minus this is going to be, sorry, not to subtract again here, sample. And then this is going to move to the right. It did. Now we need to do up and down. So I will be taking all of this and duplicate it. I will be putting a 0 here, so float 0 and float 0, but I will be switching this. And now if this is like up and down. Okay, so left, right, up and down, we already have them. The last thing that we need to do is just to add all of them and divide by 4. So we're taking the average. So add, another add, another add, and then we divide by 4. So now it's a bit blurred, and this is like the first iteration. Okay, so now what we will be doing is we will be repeating this operation. Before duplicating everything, I just want to add a few more parameters. So I'll be multiplying this by 1, and I will be coloring this or framing this in red because we're going to increase this value, or we're going to double this value every time. And I also want to multiply this by another parameter, which is going to be strength. And this is going to be an outside parameter. So this is going to be the strength of the blur. So input value, for now it can be 1. Put this in here, get float input, and plug this in here. Okay, great. And I think this I think we can try this as well. Um, but just to make sure that I'm doing exactly the same thing, I will be deleting this. And just for now, we move only left and right. So we're doing a kind of a directional blur first. This is the first pass. We're going to do a directional blur, and then we're going to do a directional blur in the vertical direction. So we add them together and then we divide by 2. And I think maybe it's just even easier to take the average. I mean average float 1. Okay, so you can see how we have like one blurred pixel. And then we just take this thing, and this is different than everything that we've done so far. This is called like a feedback loop, and uh, we need this step in order to do like an accelerated blur. So we can't put this into a loop itself. This is another kind of loop, and it's a feedback loop where you do a computation and then you store that computation and then you reuse it again. It's a bit subtle and it's different than what happens inside of a loop. Okay, so now I need to take this, and this is going to be doubled. So the strength of the blur increases exponentially. So now we blurred 4 pixels. I mean, yeah, and then here it's going to be 4, and then duplicate again, and then here is going to be 8, and then duplicate again, and 16. And by doubling every time, the strength of the blur is growing exponentially. So 32, and then 64, and then 128, and then 256, okay, great. So that was the horizontal pass. Okay, and now we're going to do the vertical pass. So I'll be taking this one and plug the output from the last iteration here and just go inside. And instead of doing left and right, we're going to just switch this. So now it's also going up. And we're going to repeat the process here as well. So 1, and then this is going to be 2, and then 4, and then 8, 16, 32, 64, 128 and 256. Okay, so this is how this is looking here, and let me just increase the strength of this one. So let me do this to like 0.5, and then take this one and bring it like, you can see there are very, this is the one that we just created, and this is the one that it's the original. So this is how uh, acceleration structures uh, can be built, and this is a very very fast way to build effects like blur nodes, and for example the min and max node also works the same, and things like that. You can do non-uniform blur, and very recently I made a blur that follows a spline and things like that, and it was based on the same principle, and you can see like it's fast, so no I mean we need to preview this one, and you can see like it's fast, no big deal or anything like that. So you would be you might be seeing like other blurs being done with convolutions, and or like just put into a while loop and averaging continuously and things like that. um this is something different, and this is how Substance Designer is doing quite a lot of its node, and it's very very fast, and it's like GPU accelerated and things like that. So I would say this is a new information, and I haven't seen it widely understood, and it's still pretty amazing what you can do with this kind of stuff. Like the distance node also works like that under the hood based on this principle, and yeah, I think uh, I think this entire tutorial has presented you with some interesting and new ideas. We've covered quite a lot. In the future, we will be diving more into while loops and what you can do with them. But in these tutorials, we covered a few different ideas. So it was way beyond the basic while loops in pixel processor, or the iteration node in the FX map. We also covered feedback loops, and also we covered the instance node. We made loops infrastructures for ourselves that allows us to just put or use any kind of nodes that Substance Designer already has. We can take them and put them into our loop infrastructure. So I think this tutorial will be useful to you. Um, and yeah, see you next time. Thank you.